Okay, so now we've learned how to model Boolean functions, we've learned how to reduce Boolean functions, we've learned how to write them up in VHDL so we can put them on our development boards and test them out. And so now it's time that we start doing something really useful. We can now start taking these functions that we've been creating and build them into a useful digital design. So you'll find that two major premises of digital design is that all of digital design is modular and hierarchical. Let's see if I can spell that, hierarchical. This means that you don't just create a huge big kludge of something. You create small little modules, which is what we've started doing, and then you start putting these modules together and you link them together in certain ways. And then you might create this bigger module. And then, you know, this bigger module can become a box. And then you might put that together with another module. Put those together, and then those become a bigger box. So that's why it becomes hierarchical, because you can take this box, expand it and see, oh, there's two smaller components in there, and then take that one and say, oh, there's two smaller components in there. And there you go. You get a modular and hierarchical design, and this sort of way of designing allows you to create complex designs without always having to go back down to the very basic simple level. You can just use designs that have already been made and put them together in your overall product. So anyway, we're going to learn a technique in VHDL called structural modeling. Structural modeling. And structural modeling takes advantage of this modular and hierarchical idea. So remember that we've been working so far on adding. And let's recall how to add a binary number. Let's say we wanted to add these two binary numbers. 1 and 1 gives us a 0, carry the 1. 1 plus 0 plus 1 gives us a 0, carry the 1. 1 plus 1 plus 0 gives us a 0, carry the 1. So there you go. We just added two 3-bit numbers. And what we did to do that was we started off with a half adder because we had two inputs, and then we needed two full adders afterwards. So in order to add a 3-bit number, we required one half adder and two full adders to make that happen. Now, we can put these together in what is known as a ripple carry adder. Now, why is it known as a ripple carry adder? Because you're taking the output of each of these blocks. The output of the half adder can give you a carry, and you ripple that carry through. So the output of the carry goes to the next full adder, the output of this operation goes to the next full adder, and so your carry sort of ripples across. So we're going to use the structural modeling technique to create this 3-bit ripple carry adder. And in your lab 5, you're going to create a 4-bit ripple carry adder. Alright, so when you're doing a structural model, you want to first draw out your black box diagram for the larger design that you want. So we want to create a ripple carry adder. And it's going to have two 3-bit inputs. Now, I haven't showed you yet, but this slash with a number represents a bus or a bundle. So I'm saying that here A is not just a single bit, it represents 3 bits. And B is not just a single bit, it represents 3 bits. So I denote that with this /3. The output of this ripple carry adder is then going to have a 3-bit sum and also a single bit carry out. Okay, so it's very important that you first create your top level black box. Now we're going to see what modules are going to go inside this box. Well, if you recall, we need to have one half adder. So this half adder you have already created. You need to draw it in such a way that it has the same exact names as you've already coded in your VHDL. So I had called my half adder, and I gave it inputs A and B and outputs Cout and sum. Now it's very important that your names are exactly the same as those names that you've already entered in your VHDL for the half adder, because the naming is going to become very important. Alright, then we're also going to have two full adders. Here's my full adder. And I had given it three inputs, A, B, and C, and two outputs, Cout and sum. And we have another full adder, which is identical to that one. Full adder. Again, it has Cout and sum as the outputs, and A, B, and C as the inputs. Cool. So now how are we going to connect these things? Well, the Cout of this first one is going to become the Cin, or the C, of the second one. Because remember, the output of this first half adder will result in a carry, which we then want to add in this 3-bit operation. Now whenever you connect modules inside a larger module, you need to give it a temporary signal name. So I'm going to call this T1. And again, the Cout of this one is going to connect to the C of this one. And we're going to call that T2. Now it's also important that you give each of these modules a name. So I'm just going to call this H1, and this one F1, and this one F2. And this is pretty much just to make sure you distinguish between, say here you have two full adders. This tells you, okay, this is my full adder, which I'm calling F1, and this is my full adder, which I'm calling F2, so that way you can at least distinguish between these two full adders. Now, how are these going to connect to the outside world? Well, these three sums we're going to stick together in one bus. So I'm going to draw it like this. And this is going to be my sum 0, sum 1, and sum 2. And those all three are going to be my 3-bit sum output, which corresponds to this up here. Likewise, I'm going to put the carries together. I think I'll draw it with another color. Oh, no, I'm not putting the carries together. Sorry about that. Because the only output really is this Cout, which can go directly out. Alright, now we have A's are going to be linked together. This is going to be A2, A1, and A0. And those are going to go all out to my 3-bit A bus. And then my B's are also going to do that. B's are going to go all together and be my 3-bit B bus. So then I can put here a dotted line around the whole thing. And this dotted line is my ripple carry adder. And as you can see, the ripple carry adder has the same outputs, cout and sum, and A and B as the inputs as my overall black box diagram. So here basically what I did was I drew the overall black box diagram and then I expanded it out to show the inner components and how they all connect together. Alright, so like I said, it's very important that your names all match with these diagrams and your code so you don't get things all messed up. So now I'm going to show you how to write this all up in code. Alright, so to do that I'm just going to open up Notepad. Here you would just be creating a new file in VHDL, a new VHDL module file. And as always, you're going to start with your entity declaration. And here, the entity that we're trying to describe is the ripple carry adder. So we're going to do entity ripple carry adder is. Now recall, once again, that your name is going to be exactly the same as the name in your diagram. Alright, then we define our ports. We have port A, which I'm saying is an input, and now it's a standard logic vector type because it's not just a single bit, it's going to be 3 bits, and to denote that it's 3 bits we say it's 2 down to 0, meaning it's bits 0, 1, and 2 representing 3 bits total. We're going to have B as an input, also standard logic vector, 2 down to 0. We're going to have sum as an output, and that's also a standard logic vector, 2 down to 0. And we're going to have our carry out, which is also an output, and this is just a standard logic. And ripple carry adder. Alright, so we've declared our entity, and guess what? After we declare the entity, we have to declare the architecture. Now the architecture, give it a name, my architecture of what? Ripple carry adder is. Now when we're declaring an architecture with a structural model, the first thing that we need to do is declare what modules are actually in this architecture. So even before the begin statement, we do what's called a component declaration. So we're going to say, what is this architecture made up of? And then we're going to list the components that are used in the ripple carry adder. So the first component is the full adder. So component full adder is, and then we list once again the ports. And you can actually list multiple inputs and outputs on the same line. So because the full adder has A, B, and C as the inputs, I'm going to write them like this. And it has sum and cout as the outputs, also standard logic. And component. Alright, now we do have 2 full adders, but we only need to declare it once because it's the same box that we're going to use twice. So we only need to declare the full adder once. But we also need to declare the half adder. And again, these names have to be exactly the same as they are in your full adder code and your half adder code. So the half adder has 2 inputs, A and B, and it also has 2 outputs, sum and cout. Oops, cout. Okay, and component. Alright, after we declare our components, we need to declare intermediate signals, intermediate signal declaration. And right now you see I'm writing comments starting with a dash dash. That's how you can add comments to your code. Now the intermediate signal declaration, if you recall, we needed to declare T1 and T2 to act as intermediate signals to connect between our components. So we need to declare T1 and T2. So we'll call these signals. So signal T1, T2 of type standard logic. Here they're not inputs or outputs, they're just intermediate signals to connect from one block to another block. So we just call them a signal T1, T2 of type standard logic. Now that we've done all that, we can actually begin our architecture. And what we're going to do is instantiate and port map the modules. So instantiate means we're going to declare, okay, we're going to use this module, we're going to give it a name, and we're going to show how it maps to everything else. So the first one we're going to instantiate is the half adder. So like I put in my diagram, I gave it the name H1. So H1, what is it? It's a half adder. And then we're going to port map it. Now with the port map, you list all the ports that the half adder has on the left and all the ports that it's getting mapped to on the right. So the first port that we need to map is A. So the A port of the half adder is going to get mapped to the A0 port of the overall ripple carry adder. The B port is going to get mapped to the B0 of the overall ripple carry adder. The carry out is going to get mapped to T1 because, as you can see from the diagram, the C out of H1 is going to get mapped to T1. And then we need the sum is going to get mapped to sum sub 0 of the overall ripple carry adder. Now it's important to note that if I had called the sum of the ripple carry adder, say something else, maybe I wanted to call it sum t or something, then down here when I'm mapping it, this would also be called sum t. It doesn't have to be the same name as this is, but it can be because they're separate modules. Alright, so I've just mapped my half adder, and like I said, you list every port in the half adder on the left, whether it's an input or output, and then you list where it's getting mapped to on the right. Okay, so we've mapped our half adder. Now we need to map the first full adder, so gave it a name F1, which corresponds now to this full adder. So full adder port map. I think what I'm going to do to make this easier is just copy this. I'm going to call it full adder. And now this one has a C input as well. And what does that get mapped to? See if you can answer it before I tell you. This C input gets mapped to T1. So that's why you need that intermediate signal, because you need a signal to map the output from this to the input of that. So that gets mapped to T1. The C out of this one is going to get mapped to T2. Here's the C out getting mapped to T2. And the sum of this one is going to get mapped to sum 1. And the A and B's are also going to be A and B sub 1. So it's the second bit that we're adding. Alright, then we need the last one, F2, which is this full adder. That's now going to get mapped to the third bit. The C input is getting T2, which is this guy coming in. And the sum is going to sum 2. So this parentheses so when you would say this as sum sub 2, which means that sum is a bus, it's a bundle of bits, and then this specifies which bit in the bus it is. So because this is a 3-bit bus, here this is the third bit, or sum sub 2, this is the second bit, or sum sub 1, and this is the first bit, which is sum sub 0. All those go into a 3-bit bus. Alright, so we've mapped everything, and then we just end the architecture. End my arc. And there you have it. You've just created a ripple carry adder. You didn't have to recreate the half adder. You already made it. You just made use of something you had already created to make a larger module. Now this ripple carry adder has two inputs and two outputs, and now these can get mapped in your implementation constraints file to the actual board. So you can map 3 inputs, 3 switches to A, 3 switches to B, 3 LEDs to sum, and 1 LED to see out. So typically your uppermost module, or the biggest black box that contains everything, is going to have all of the signals that connect to the outside world. Everything on the inside doesn't connect to the outside world, doesn't need a separate UCF file. The only thing that needs the UCF file is the outer module that connects to the outside world. So when you add this to your project, you would add this VHDL file, which has the ripple carry adder, and you'd also include the 2 VHDL files that you've already created, one for the half adder and one for the full adder, and make sure that all your naming is consistent.